We're going to explain the Float On lab. When we finish this PowerPoint, when we finish this, you should be able to distinguish between intensive and extensive properties. You should be able to relate significant figures to the equipment accuracy. You should be able to perform calculations using significant figure rules and use the equation density equals mass divided by volume. Now, with the modeling clay, we're looking at the things that changed. The mass of the modeling clay will vary depending on how much modeling clay was actually used. How much you actually picked up, that's going to vary depending, and it'll change the mass. And not everybody's going to pick up the same amount. Everybody's going to pick up different amounts. So we shouldn't have the same mass in either of the groups because there should be a difference because everybody picks up a different amount. Another thing that will be different, another thing that will change is the volume. The volume of the modeling clay varies depending on how much modeling clay was actually used. So when you look at the volume of the different shapes, each one of them will be different because depending on how much modeling clay was used to make each shape, that will change the volume of it. And what we call these things, like mass and volume, is we're going to call these things our extensive properties. Okay? And those are properties that vary depending on the amount of sample, of the amount of what we actually have, what we're actually looking at. Some other extensive properties are going to be length. That's an extensive property. It's a measure of distance from one end to the other end. Mass, we already talked about that. It's the amount of matter in an object. We can look at area. Area is an extensive property, and it measures the two dimensions of length. If we're measuring the area of a rectangle, we would multiply the length and the width, the measurement of both of those. Volume, we talked about that. We know that that's an extensive property, and it measures the three dimensions of length. So our length, our width, and our height. And then weight, that would be an extensive property, and that's just the force of the downward, the gravity downward caused by the earth. Okay, so those are extensive properties. Now, the things that don't change, what we should see is in looking at the modeling clay, the density of the modeling clay should remain constant or pretty close throughout the entire experiment. It really doesn't matter what volume we have. It really doesn't matter what mass we have. But we know that those are going to work out in proportion, and it's going to end up with pretty much the same density. We call those things intensive properties. And those are properties that do not change if the amount of the sample changes. So if we have 10 grams of the modeling clay or we have 1 gram of the modeling clay, it should have the same density throughout. Okay, some other intensive properties. We can look at boiling point or melting point. Any of those are going to be the point at which matter changes state. We can look at specific heat capacity, which is specific heat is going to be the energy required to change the temperature of 1 gram of substance 1 degree Celsius. We can look at things like malleability or being ductile. Those are going to be intensive properties. And then we can see going on down the list, we have solubility, pH, color, viscosity, reactivity, conductivity. Those are going to be things that do not change no matter how much or how little of the substance we actually have. Now, example A1, it says a forensic pathologist obtains a sample of an unknown chemical taken from the home of a murder suspect. The sample initially, which is 100 milliliters, spills as it is being transferred to the lab, leaving only a 5 milliliter sample. What properties can be analyzed by the pathologist and hold up on cross-examination? When we're looking at this question, the one thing we have to understand is that the majority of the sample is actually lost. Okay, 95 milliliters of the sample is actually lost or spilled. So only 5 milliliters of the sample is actually left. Okay, so we cannot have any properties that are going to have to depend on the amount of material that's there. Okay, the only properties that are going to remain are going to be intensive properties, such as density, or the other intensive properties that we went over. Okay, those are the only things you're going to be able to hold up in court because they do not depend on the amount of matter that is there. Okay, example A2. When we're looking at this, it says which of the following properties would be best in determining the identity of an unknown substance. Remember here we are looking for intensive properties. Extensive don't help us identify unknown substances, so here we're looking for intensive properties. Okay, it says which of the following properties would be considered an extensive properties. Make sure we look back at our list and we find the answer for this one. Measurements are incredibly important to science. In fact, they're mandatory for all sciences. Measurements are what we use to actually figure out what we have. If you can't measure it, then it never happened. There's many different ways that we measure. We can measure length, as in yard or inches, the metric system where we use meters, kilometers, or we can measure volume. We can measure in different ways. Tablespoon, cup, pint, quart, gallon. That's measurement of volume. Or we could look at mass when we have to deal with ounces or pounds. And now, in the measurements that we use in science are going to be the metric system. So for length, again, it's going to be meters. When we look at volume, it's going to be liters. And when we look at mass, it's going to be in grams. Now, there are two things we're going to look at when we're dealing with measurements to figure out what type of measurement we have. The first thing is accuracy. Accuracy is getting the correct value of the measurement, getting the right answer. So if we had a 5-gram sample of aluminum and we put that on a balance, we would know that we were getting an accurate measurement if the balance read 5 grams. If it didn't, then the measurement or the balance would not be accurate. We can quantify this with percent error. So when we look at our percent error, we know what we should get, we know what we actually get in the lab, and then we can compare those and see how far off we are. Okay, when we're looking at accuracy and when we're trying to measure, we include all numbers on an analog instrument and then one estimated digit. So if we're looking down here, we're measuring this rock, we see that we're measuring the length of it. What we would do is we would see that, well, we know it's in between 1 and 1.5. We can go even farther because we know that this is broken up into 5 different sections. So we know that it's 1.1, we know it's 1.2, 1.3. It's not quite 1.4. So what we can say for sure is we know it's 1.3. And then we estimate one digit farther, which it's kind of right in the middle of 0.3 and 0.4. So we're going to measure it out to 1.35. And that's going to be our measurement. We always estimate one digit after what we can. Now, the other thing that we use to look at measurements is we look at the precision of the instrument. Precision is obtaining the same measurement repeatedly. Okay, so if we had that 5-gram sample of aluminum and we put it on the balance and it read 4.0, we know that it wouldn't be accurate. But if we took that same 5-gram sample, took it off the balance, re-zeroed the balance, and put it back on, and say we got 3.9. Okay, it's still not 5, but we take it back off, we re-zero the balance, and we put it back on again, and say we get 4.0. Now, all those measurements are around the same thing. They're all around 4. Okay, so what we can say is that we can say that that balance is precise because it's getting around the same measurement every single time. Now, all instruments are going to have an uncertainty in the measurement, meaning we're not going to always get exactly what we should get every single time. In chemistry, if you get 0% error, you probably did something wrong because there's always going to be a little bit of inaccuracy, or it's not going to be as precise, the instrument that we want it to be. When we're looking at precision, we can quantify using standard deviation, meaning how far apart are our numbers. Now, significant figures. Significant figures are used so that we do not misrepresent the accuracy of your calculations. We use significant figures because, say we take density for instance, we'll take the mass on a balance, we'll take the volume, usually with a graduated cylinder, and what we'll get is we're using two different instruments, so we have to make sure that we're using the accuracy of the least precise instrument. So if we're using a graduated cylinder that's not very precise or accurate, we have to use the least amount. And so we can use a really good balance, but if we don't use a really good graduated cylinder, then the reliability of our density has to be based off of the not so good graduated cylinder. Some rules that we have for this. All non-zero digits, meaning anything 1 through 9, are always significant. So say we take the number 524. Okay, we would have 3 significant figures because they're all non-zero digits. It's 1 through 9. Okay, so in that number 524, we have 3 significant figures. Now, 0 between non-zero digits are always significant. So if we're looking at this and say we have 105, okay, we know that our 1 and our 5 are going to be significant because they're non-zero digits, but this 0 in the middle is going to be significant as well because it's kind of sandwiched in between 2 non-zero digits. So in this number, again, we would have 3 significant figures. Continuing on, our next rule is leading zeros are not significant. So say I have 0.0256. Okay, we know that all non-zero digits are going to be significant, so the 2, the 5, and the 6 are going to be significant. But since these zeros are in front, we call them leading zeros. They're not significant. So in 0.0256, we only have 3 significant figures. Moving on to the next rule. Zeros to the right of all non-zero digits are only significant if a decimal point is shown. So say we have a number of 400.0. When we're looking at this, again, the 4 is going to be significant, but we have to look at the zeros. The zeros are only significant if the decimal point is shown. So since there's a decimal point right there, all these zeros are going to be significant as well. So we would have 1, 2, 3, 4 significant figures in that number. But if that decimal point was not there and it was just 400, since there's no decimal point, those zeros are not significant. So we only have 1 significant figure in that number. Okay, our last one that we have is for values written in scientific notation. The digit and the coefficients are significant. So say we have 4.30 times 10 to the 15th. All we would consider for our significant figures are the numbers up here in the coefficient. Okay, so it's 4.30. The 4 is significant, the 3 is significant, and that 0 is significant. So we would only have 3 significant figures in that scientific notation. Now, when we use these numbers in multiplication and division, addition and subtraction, we also have some special rules that we have to follow. In addition and subtraction, okay, so just in addition and subtraction, if we're adding or subtracting 2 numbers, we line up the digits according to the decimal point, and we round the digits with the lowest number of decimal points. So if we're looking at our example over here, what we can see is that we have our 101.25, and we have our 3,536.2, and 123.448. And if we're adding those together, we use the least precise number. Okay, this only has 1 digit after the decimal. Okay, the 101.25 has 2 digits after the decimal, and the 0.448 has 3. So we have to round to only 1 decimal place. So that's why in this answer we get 3,760.898. We would round to the least one, which is just 1 decimal place. And so we would round to that 8, which that 8 rounds up to a 9. That's only for addition and subtraction. With multiplication and division, we determine the number of significant figures in each term, perform the multiplication or division, and round so that the answer has the same number of significant figures as the lowest significant figures term. So if we're looking in the very beginning, what we're going to do here is we have 34.6, which that has 3 significant figures. 12.1 has 3 significant figures, and 1.2 has 2 significant figures. So what we do is we multiply all those together, and then we have to round to 2 significant figures. Okay, so we know that this first number is significant, that's 1, so we're going to round to where we have that one, 2 significant figures. So we round it and we put it in scientific notation when we're finished, and we get 5.0 times 10 to the second. Example B1, it says, in the lab you heat a 9.678 gram object with a specific heat of 4.18 joules per gram degrees Celsius from 2.345 to 22.34 degrees Celsius. How can you accurately report the heat gained by the object using the formula below? So when we're looking at this, it's a complex equation. We're going to use it a lot when we get into thermochemistry, but basically all we're looking for is we're looking for the heat gained. And all we have to do is multiply the mass by the specific heat times the change in temperature. Okay, so the first thing we have to do is let's find the change in temperature. And that's real simple. We have 2 temperatures right here. And the change in temperature, all it means is going to be our final temperature minus our initial temperature. So when we look at that, we're going to have our 22.34 minus our 2.345. And when we do this, remember what we want to do is we want to line up our decimal places. So we line them up, and we remember, since we're subtracting here, we have to do it to the least number of decimal places. So our answer is going to be 19.995. So the least number of decimal places is going to be to our hundredths place right here. So basically we round to the hundredths place, which that would round everything up to just straight up 20.00. And that's going to be degrees Celsius. That's going to be our change in temperature. That was the hard part because we had to look at that. So all we're going to do now is we have our 20 degrees Celsius, and that's our change in temperature. And then all we have to do is multiply that by our mass, which our mass is going to be our 9.678 times our specific heat, which is 4.18. And remember our units here, this is grams and this is joules, grams, degrees Celsius. We multiply all this together, and now we're multiplying. So remember, the rules for multiplication is the least number of significant figures. When we're looking at this, our answer is going to end up being 809.0808. Okay, so when we're looking at this, what we'll see is our least number of significant figures. This has 1, 2, 3, 4 SigFigs because they're all non-zero digits. The 4.18 is going to have 3 significant figures because they're all non-zero digits. And then our 20.00 is going to have we know the 2 is significant, and the zeros are following a non-zero digit with a decimal, so therefore those are significant as well. So 1, 2, 3, and 4. So the least number of significant figures is going to be that 3. So we round to 3 significant figures. We know that the 8 is significant. We know that the 0, we have to have that because it's going to be sandwiched in there. And the 9 is significant. So we're going to round to that. The 0 doesn't round it up. So accurately reported, we're going to have 809. And in this case, our answer would be in joules. looking at example B2. It says perform the mathematical operation shown below and report your answer to the proper significant figures. Remember, when we're working this out, make sure that you do the parentheses first. Follow the rules for multiplication within the parentheses, and then you're adding and subtracting. Make sure you follow the rules for addition and subtraction with significant figures. You should get an answer right around 67. Okay, guys, on B3, make sure that you work this one out following your rules for significant figures, and you should get an answer of 157.9. Now, density. Objects can be identified by the ratio of the mass and the volume, and that's what we call our density. Our density is constant for all homogeneous mixtures, and what we see here is that when we're looking at our density, it's going to be an intensive property, meaning it doesn't change no matter how much material we actually have. And we can use density to help us sort out what we have. You can see over here, here's a nice density column, and we can see that all of these different liquids going throughout this density column. So we have a bolt down here, and then we have our honey, and then we keep on going up. And the reason why they're able to separate out into these different layers is because of the different densities. We also use density if you ever put something in a centrifuge. What we see is that it spins around in a very fast circle, and all the more denser particles will float to the bottom, and we can use that to separate things out. Now, the equation for density is going to be density equals mass divided by volume. We should be able to manipulate this equation to solve for any variable. So if I wanted to solve for mass, all I'd have to do is multiply both sides by volume. So we get mass equals density times volume. And if I wanted to solve for volume, I would just switch places with density and volume, and I get volume equals mass all divided by density. And these are the three equations that I could possibly get when I'm trying to solve for different variables in the density equation. Things that we need to know about it. Density, it's the degree of compactness, or the ratio of the mass of volume. That's the definition of it. The SI unit is actually kilograms per meter cubed. But in chemistry, we use the variable, which we'll always have, is grams per cubic centimeter. One thing I'll point out here is that cm3, that's a cubic centimeter, also equals 1 milliliter. That's why we use a graduated cylinder to find the volume. This is always, when we want to find it, it's always going to be calculated. Now, the volume is the amount of space taken up by an object. Again, we see the SI unit for it is meters cubed. Remember, in chemistry, we'll either use cubic centimeters, which equals 1 milliliter. We usually can use a stick or a graduated meter stick or graduated cylinder to find the volume. Mass is the amount of matter. Its SI unit for it is kilograms, but in chemistry we will use grams. And we can either use a triple beam balance, or we can use an electronic balance to figure out our mass. Now, the density has a great effect on the states of matter. Matter will be broken up into basically how dense the particles are. How far apart the particles are will tell us the density, and it'll tell us what state of matter. There are three common states of matter we see every day. We see solids, we see liquids, and we see gases. But there are 6 recognizable states of matter in the scientific community. We have solid, liquid, gas, plasma, Bose-Einstein condensate, and a fermionic condensate. Those are the 6 recognizable by the scientific community. We usually focus on the 3 common states, solid, liquid, gas, and we throw in plasma in there as well. Now, all these different states of matter vary in the density, so how dense they are, how far apart the particles are, and compared to the mass of it. Now, in a solid, that's the state of matter in which object has a definite shape, definite volume, and very little movement of the individual particles. Generally, it's the most dense state of matter, And what we see is that basically all the particles will be very, very close together. They're moving, but they're kind of just vibrating in place, and they don't have the free movement of a liquid, but they kind of stick together. The next state of matter is a liquid. It has an undefinite shape or undefined shape and a defined or definite volume. It's free movement of individual particles. Because the particles are able to move and able to flow, we get fluids, we get liquids. It's less dense than a solid, with the exception of water. We see that ice floats on water, so water is an exception to that, but it has an undefined shape, definite volume for the liquid. And then to deal with gases, the next common state, we usually talk about the kinetic molecular theory. And we're going to talk about it very quickly and put the postulates out there for you. But when we're dealing with gases in general chemistry, we have to deal with ideal gases. And so usually we set parameters for how we deal with those gases. The first postulate of the kinetic molecular theory is that a gas consists of small particles traveling in a straight line motion and obeying Newton's law of motion. Basically, they're moving and they're following all the laws of Newton's, all the laws of motion. The next thing is that molecules of a gas occupy zero volume, so they're not going to have any volume. And collisions between the gas molecules have zero energy transfer, meaning when the gas molecules actually collide into each other, one of them doesn't speed up or slow down. They just all stay the same movement. And there are no attractive or repulsive forces between the molecules. As they get closer together, it's not like they push each other apart like magnets do when you have two like poles. And then lastly, the average kinetic energy of a molecule is defined by 3/2 of kT. Now, all of that said, it leads us to our gases, and we use those postulates to look at gases. Now, gas is a state of matter which we have an undefined shape, undefined volume, and we have free movement of individual particles. They can move all around, and they follow the postulates of the kinetic molecular theory. And they're less dense than solid in a liquid. So as we've gone from solid, liquid to gas, we're getting less and less dense. And then the next one we have is plasma. And a plasma is a gas that has had electrons removed so that it has an undefined shape, a definite volume, and a free movement of individual particles. Now, when we're looking at this, the main difference between a gas and a plasma is that a plasma has fewer electrons in it. When we're ranking these, remember we're ranking our phases. Solid is the most dense, and then we have liquid, then we have gas, and then we have plasma. Remember that water is an exception to the above rule. We have to have water, which actually the ice floats on top of the water. Now, all of this leads, we have to know our phase transitions, meaning as we go between one phase to another. When we go from a solid to a liquid, we know that that's melting. When we go from a liquid to a solid, we know that's fusion, or we can say that that's freezing. When we go straight from a solid to a gas, so we're skipping over the liquid phase, we call that sublimation, and going straight from a gas to a solid, we call that a crystal lattice formation. And then anytime we go from a gas to a liquid, we have condensation, and from a liquid to a gas, we have vaporization, or next to vaporization, you can put boiling. All right, let's look at example C1. It's a big question. It says you're trying to make an unknown cube float. Unfortunately, the cube does not float in water, so you must use an alternative liquid. You record the mass of an unknown solid to be 456 grams, and the sides of the cube measure 4.5 centimeters. You have 3 liquids from which you can choose based on the graphs which would be the best choice. So we're trying to make it float. And when we're looking at it, it does not float in water. So we know water is going to have the density of 1.0 grams per cubic centimeters. So it doesn't float in that. So the first thing we have to do is we have to figure out if it doesn't float in 1.0, what's its density? So it's got to be more than 1. So what we do is we have our mass right here. And we know our equation for density is going to be density equals our mass all divided by our volume, right? So we know that that's our equation. So we have our mass, and we see that we have a measure of 4.5 centimeters, and it's a cube. So to find the volume of a cube, all we have to do is 4.5, and we cube it. So it's 4.5 times 4.5 times 4.5. And when we do that, we'll get a volume of 91.125. And we'll use our SigFigs here and round it, and it'll just be 91. So what we'll get for our equation to find the density of the cube, our density is going to equal our mass, which is 456, all divided by our volume of 91. And rounding to 2 SigFigs, we're going to get a density right around 5.0 grams per centimeters cubed. Now, this is going to be important to us because when we look at the different graphs, we have to find something that's going to float. So basically, what we need is we need to have something that is more dense. The liquid has to be more dense than 5.0 grams per cubic centimeters. So in looking at our graphs, what we can see is this is going to be a mass versus volume graph. And anytime we have a mass versus volume graph, we have mass on our y, volume on our x. What we can see is that we always use the equation of slope. And if we find the slope of this line, what we'll see is that it'll have the density. So when we're looking at it, we can find the slope of these 2 points. There's 2 points, and we'll do our y2 minus y1 over x2 minus x1 to find our slope. And basically what it's going to end up being is we'll have our density. Here's our mass, which is going to be 10 right here. And then our volume at that point would be 4. Okay, so we would get our volume there, or get our density there, and our density would be 2.5. So we know that it couldn't be liquid A because liquid A is not over 5. Okay, so let's move on to the next one, and we'll do the same exact thing. Liquid B. When we're looking at that, again, here's our mass. Here's our volume, because remember, using slope, and the first point is going to be 0, 0. And so what we get is we get our density equals 10 all divided by 2. And we see that that will give us a density of 5, but we want it to float, so therefore it has to be greater than 5. So we look at our last one of what we have, and again, we find the slope, and we have 10 and 1. So density equals 10 all divided by 1, which that will give us a density of 10 grams per cubic centimeter, and it's larger, so we know that this cube would float in liquid C. Okay, looking at example C2, it says a farmer is trying to take home liquid fertilizer in an 825-gallon container. He knows the fertilizer will have a density of 1.58 grams per milliliter, and the max cargo of his truck is rated for 2,500 kilograms. Will the farmer be able to safely transport the fertilizer home without breaking his truck? Main thing here you have to understand to be able to work this one out, the mass cannot exceed 2,500 kilograms. So what you're trying to do is you're going to use these two numbers, the 825-gallon container and 1.58 grams per milliliter, your density, and you're trying to find your mass. Remember that mass is going to equal our density times our volume. Main thing to pay attention on this problem, this is gallons, this is milliliters, this is grams, this is kilograms. The answers you should get should be no. You should be able to tell me the number. Example C3, it says the following data is taken from the lab. We see that we have a height, a diameter, and a mass. And it says what is the density of the unknown object. Use your height and your diameter with this equation. Volume equals pi r squared times our height. That'll give you the volume. Here's your mass. Go ahead and find your density. Example C4, you place a solid piece of iron into a specially designed beaker. The beaker is then put over a very intense flame. Describe the density of the metal as heat is continually added to the iron. The answer that you should get is that density decreases. You should be able to tell me why.